So Assalamu alaikum students, welcome again to our online lecture series right after this corona episode. Hopefully the situation would get better soon and we will be able to sit together in the class again. This is our second week after the midterm of hydrology and water resources management, and today inshallah we are going to look into a subject, or let's say the topic of stream flow. Before the midterm period and the last week lecture as well, we looked into the evaporation and transpiration process, and this evaporation and transpiration process was one part of the bigger hydrological cycle. So we will be basically looking into the most important component of the hydrological cycle, which is the discharge or the stream flow. And regarding discharge or stream flow, we will be looking at the definition of it, what is water stage and how the water stage is measured. We will be looking at different tools that are usually used to measure the stage. Stage is basically just the depth of water. So whenever I am referring to stage, you should understand that I am referring to the depth of water. So we will be also looking at the selection of site for stage recorder, how do we control and meter the cross sections, and then importantly, what are the different methods of measurement of stream flow. You would understand, and we will see that there are different kinds of cross section of stream flow, which some of them are easier to measure, and some of them are a little bit complicated to measure discharge in. So we will be looking at different methods that are available to us. We will also be looking at the interpretation of stream flow data. We might not go into the full details of it, but we will try to just touch upon it as is mandated in the course contents by HEC and also our own university. We might not touch upon the return period because this is a topic, or let's say this is the part of the lecture which is not included in the HEC course content that is being given to us, but anyways we will touch upon it in a very cursory manner, and we will see how it is used. Return periods are then studied in detail in other subjects. The references that I am going back to in this lecture series, and also the contents that I have included in this lecture, are basically from these sources. The two books that I've already shared with you, the details are given in the LMS on the course page. Also, when I was in Germany and I was going through the similar topics, I've collected some material from there also, and also from other universities that is online available. So I'm referring to them in few slides. Okay, so hydrological cycle, we have looked into it in quite detail in the initial lectures. We have studied the evaporation and transpiration, we have studied precipitation, we have gone through the meteorological part of it, how precipitation is made and how the precipitation, or let's say the cloud travels, and what are the conditions of precipitation, and all those kind of things. Today we are concentrating on runoff. So sometimes we will be referring to runoff, sometimes we will be referring to stream flow. Both of the words are used or can be used interchangeably. But anyways, runoff or stream flow is basically any catchment's reaction to an event of precipitation or to the general drainage of a certain catchment. So a catchment can be reacting to a precipitation event and there would be discharge, or maybe there is no precipitation there, but still, because the drainage is occurring and there is groundwater flow and different things, so still we see that there is a runoff in the rivers or in the streams. So we will be looking at these things in this lecture. Streamflow runoff is basically the overall volume of water that exits a certain drainage basin through a particular point, which is considered as the outlet point of that catchment or watershed or a drainage basin. Again, three different names, but they are used interchangeably: the watershed, the drainage basin, and the catchment. They are used interchangeably and they mean the same thing. So whenever we have a certain drainage basin and there is drainage occurring from that basin and the water is getting out of that particular area through a certain point, that discharge is called the runoff, and we measure it and we use it for different engineering studies. In engineering hydrology, we are basically looking at how to measure the discharge so that we can properly manage the water resources that are available to us. And in current time period, looking at the climate change and different other things and the use of water, the unsustainable use of water, this topic becomes even more important, so that we know how much water is available to us. Anyways, so runoff is done, there are different parts of runoff: the surface runoff, the interflow, groundwater flow, direct runoff, effective rainfall, and base flow. Through the course of this lecture, we will be differentiating between each one of the component of runoff, and these things would be understood. So let's see how we summarize or how we make the whole process easier for us. You see, we have this hydrological cycle, and for our understanding we try to make the whole thing a little bit easier for us, and we divide each and every process into different components. We say that there is a precipitation occurring. That precipitation is then introduced on a certain surface system. There is an interchange of water between surface and groundwater system through the soil system. So there is a lot of things are happening here. The infiltration rate and the speed of water through which the water infiltrates the groundwater and then reaches finally the groundwater reservoir. So there are a lot of things that are happening here, and then from each surface there would be evaporation occurring, depending upon the situation, depending upon the ground conditions. But anyways, whatever the thing is, ultimately we also see different parts of the runoff. There is a surface runoff, interflow, and groundwater discharge. Surface runoff is that part of the runoff which directly, so precipitation falls on a surface, and without going into the soil system, it directly drains to a certain reservoir or to a certain stream. Interflow is that part of the runoff which enters the upper part of the soil system, and without reaching the groundwater system, it flows inside the soil system and reaches the stream and contributes to the stream flow. Groundwater is basically that part of the flow which reaches the groundwater reservoir, and very slowly it contributes to the surface water. And all of them, when are combined, they are called as discharge. Ultimately, whenever we are measuring the discharge at a certain point, at a certain location, that discharge contains the parts from surface runoff, from the interflow, and groundwater discharge. So this thing should be understood. I'm not going into the details of the retention or what this triangle means here, but just consider it as the time that each component of the surface runoff takes to reach or to change into the discharge. So surface runoff, you see, is very short time it reaches the discharge or converts into discharge very quickly. Interflow takes a little bit longer, but it comparatively it reaches discharge or converts into discharge also rather early. Groundwater is that part of the precipitation, or let's say that part of water which contributes at the very end to the discharge volume. So as we said, we have a certain watershed. The watershed is drained by different streams, by different rivers. They combine into one bigger river, and there is a defined outlet point through which we measure the discharge. So basically, discharge is a volume of water that is passing a certain area or a certain plane in a certain unit of time. You already know the formula for discharge, which is the velocity into area. In fluid mechanics and also in hydraulic engineering, you would have gone through the piped flow, and in piped flow we have a constant cross-sectional area. In open surface flow, usually we have a problem that our cross-sectional area is not defined, or it is very let's say non-constant. So the area is not constant. You cannot measure the area very easily. There are a number of undulations there, so it is difficult to calculate the area there. So this is one part where we have to look into when we are calculating or measuring the discharge. Average velocity can be measured by different techniques, and we'll see what are the different methods of measuring the average velocity, so that we can multiply it with the cross-sectional area and compute the discharge. The units of the discharge and velocities is usually we use the cubics or Q6, or let's say the cubic feet per second or cubic meters per second. Velocity associated with them are obviously then in either feet per second or meter per second, and also the area would be in square meter or square feet. So these are the units that are generally used in the open surface flow. Of course, there are liter per second or gallons per second. These are other units, but in open channel flow, in stream flow, usually these are the two most important, the two most widely used units: the cubic feet per second and cubic meter per second. Now, a discharge is usually represented by a hydrograph. Hydrograph is basically a pulse of a certain stream. In fact, the discharge in itself discharge in itself is a pulse of the whole catchment. So whatever is occurring in the catchment, you would be able to find out that in your discharge. If you have a very good record of discharge with a relatively higher time resolution, so sometimes even small changes in the catchments can be observed by just looking at the discharge data. So discharge data is usually called as the pulse of a catchment, and similarly this discharge is usually shown as a hydrograph. Hydrograph is just the stream discharge in any units versus the time. Time is on x-axis and the discharge is on y-axis, and there is a typical shape of a hydrograph, and we will be looking at these different parts of things. So you see the line here is a little bit decreasing before there is a kind of storm here, there is a little bit in decrease here, and then there is an increasing limb, a decreasing limb, and then returning to the normal situation. This initial part of the curve is called the base flow. This base flow is basically the sustained stream flow of a certain river or a certain stream. You would have observed in your areas that even when there is no rain, there is certain amount of water that is going in the river. Certain streams would be flowing quite heavily, some of the streams wouldn't be that heavy, some of the streams would be reacting very quickly to the precipitation events, some of them are not reacting that quickly to the precipitation events, but there would always be some flow in perennial rivers. Perennial rivers are those rivers which are flowing all over the year, whether there is precipitation or no precipitation. So that minimum discharge that is always there in the river, you can call it a base flow. In lowland streams or in areas which are plain, base flow or the amount of water that is being flowed in that is flowing in the river is sustained by the groundwater. So as we said, we have a groundwater component, and when there are favorable condition, that groundwater would contribute to the stream flow. So the water that is flowing in this river, for example, is contributed heavily by the groundwater, and this is typical of the catchments which are in lowland areas or the plain areas of a certain area. In higher elevation areas where the topography is usually high, the base flow is composed of water that is coming from the snow melt or glacial melt, including the groundwater as well, but the major component is coming from the snow melt or any water that is stored there in other forms. We see then a rising limb. So whenever there is a certain event occurring, initially we had this catchment where the flow was occurring, but now we have a certain event of rainfall, and that rainfall, when occurs on a certain catchment, would obviously contribute to the increased discharge. That increased discharge is shown by the rising limb. And when the rain stops, of course, that water, the catchment would then tend to become normal again, and it would again reach to its base flow situation. Increasing limb is that part of the hydrograph where almost all the catchment, or let's say most of the catchment, is contributing to the stream flow. Once the rainfall stops and there is no more input of additional water to the catchment, the further areas where the rainfall has fallen would also then start contributing to the stream flow, and that part would also then reach to this point, to the outlet. And usually this is the point where we see this receding flow or the falling limb of the hydrograph. And once almost all the catchment has drained, even the water that has fallen on the furthest area of the catchment, when even that water reaches to the outlet point, again we would be in a normal situation and the base flow would start again. So we would be again more or less equal to the point where the discharge has started increasing. So these are three different parts of the hydrograph. At this level, at undergraduate level, it is enough to understand that there is a thing called hydrograph. Hydrograph is a kind of time series of discharge with x-axis containing time and y-axis containing the discharge, and that there are different parts of the hydrograph which are associated with the different processes that are occurring in the catchment. Now, how do we measure discharge? As we said earlier, we have to have a certain area through which the water is passing. We should know what the area is. Then we have to determine the velocity that is flowing in that area. We'll multiply these two things and we'll get the discharge. Yeah? Seems very easy, and in fact it is easy. There is nothing much in it, but we have to understand that there are the velocity. As we said, that we have to compute the average velocity. The reason is that velocity, and you would have observed it, velocity doesn't remain the same throughout the cross-sectional area. There are areas where the velocity is higher, and there are areas where velocity is comparatively very low. As you can see here, we have areas of higher stream velocities, and then there is an area of low stream velocity. Within the higher stream velocity area, we have a certain point where the velocity is the highest, and then going across or going along the cross-sectional area of a river, you would see that the velocity is decreasing as we reach to the bottom surface. And that's the reason that we have to compute the average velocity. We do not want the highest stream velocity, which is here in top in the middle. We do not want the lowest stream velocity. We need average velocity, and that's why and you would see now that when we are computing the velocities, these velocities have to be computed at different areas, and then the average velocity has to be taken and multiplied with the cross-sectional area. We use different principles for measurement of velocity. We have a point measurement of velocity through the current meter, or we have integrated velocity measurement structures or tools, for example weirs, ultrasonic methods of measuring the discharge, and trace and dilution method. As we said, we are going to compute the average velocity. What we basically do is that we compute velocity throughout the width of a certain stream flow, and then we are computing velocities at different depths. So we would reach to a certain point, and we lower our tool that we are using for velocity. For example, current meter, which is one tool of measuring the velocity. We'll lower that tool to the certain depth. We'll calculate the velocity, or we'll use the data and then convert that data to find out the velocity. And we do this at different depths. We move along the width, we do again the measurements, move along, take the measurements, and similarly we compute the whole thing. And we take the average of the velocities and compute it with the area or the width. This is a basic shape of current meter. You see you have a guiding vane here and then a revolving part here. This part is usually the one which is facing the water, and the revolutions that are recorded are then converted into velocity. This is a basic current meter tool that usually is used for finding out the velocity. We can, of course, use that current meter in different situations. We can use it through propellers, or we can suspend it on a rod or from a rope which is being hanged along the width of the river, and we can then take the measurements of the current meter. So you see here the guy is standing here and he's taking calculating the velocity. You have to make sure that you yourself are standing in the downstream direction, and your current meter is in front of you facing the incoming water, so that there is no obstruction to the velocity when you are measuring or taking the data. There are certain cableway installations also usually being installed along the river, which usually have automatic system, and usually they compute the velocities at regular time intervals at regular depths along the width of the river section. Sometimes we also need to have a matrix of the velocity along a certain area. So for example, let's say you have this much area, a turbine outlet for example, and let's say the whole area is filled with water and water with very high velocity is flowing through it, then you have a complete matrix of current meters installed all around the area, and each one of them is then connected to a certain system, and you can get the velocities at each and every point. Usually these are done in the tunnels for the hydropower systems or hydropower projects, in the dams, and other projects of the same sort. And then finally we get a flow field for the velocity all along the area in which the water is flowing. So you will see that there are higher velocities here, for example reaching 1.25 meters per second, and then comparatively low velocities of 0.15 meters per second near the boundaries of that cross section. Of course the velocity is decreased because of the frictional losses that are occurring inside that structure. There are then other installations, the weirs for example, the spillways or other gauges where we can compute the discharge, because we know that a certain, for example when we are looking at this picture, we know that okay, there is a consistent depth of water, we know the height of this structure, we know the width of that structure, so we have a fairly good idea of what the area is, and then we just compute the velocity and we can compute the discharge along the river. So weirs are another way of calculating the discharge. Sometimes we have problem of this sort where you have an area which you cannot compute. I mean, if you look at this area, for example, there is a certain stream which is flowing and it is meeting a bigger stream or a bigger river here, and you want to compute the discharge in this stream now. So how are we going to compute the discharge in this stream? Of course, you do not have an area which is very defined. You cannot compute the area here because of the nature of this area. We have then other methods of it. One of them is the tracer dilution method, where we introduce a certain tracer with a known concentration in the upstream part, and we introduce that tracer or that chemical or in the upstream part with the constant injection rate, and we then measure the same thing downstream, and we try to find out the concentration which is here, and then because we know what discharge, or let's say what was the amount of tracer dilution that we introduced into the river, so that is already known. The concentration is also known. We have the other values, and we can then find out the discharge. For example, let's say you have initial concentration with a certain discharge that you have introduced into or the discharge, or let's say the volume of the tracer that you have introduced, and then you have the downstream condition where you have the river discharge, the tracer discharge that you have introduced. This value is known, this value is known, these values are known, the only unknown is then this one, and then we can compute the discharge. So usually this method is used for the areas where the cross-sectional area is difficult to compute. Once we have the depth of water, and we can calculate the discharge. For example, we took we calculated the velocities, we calculated the discharge, and while we were calculating the velocities, we also had the depth at which we calculated the velocity. So we have fairly good idea of what the water depth was. So what we can do is that we can relate the two things. We can relate water depth to the discharge, and we say that when the water level was this, for example, then the discharge was this. When the water level was, for example, this thing, then the discharge was equal to this value. So we have this observed values, these observed values here, the measurements. These crosses are basically showing us the measurements that we took, and then we can fix a line to those measurements. We can say that okay, these measurements can be fairly depicted or can be fairly represented by this line. So This line then is called a rating curve. You have a rating curve between water depth and discharge, and this is then a guideline for you for that particular area for measuring the discharge. You do not have to go all the time and calculate the velocities. If you have a normal condition, normal flow going on, then we can just simply calculate the depth, and we take we can come back to this curve and calculate the discharge. You can go through these things when the slides are uploaded on the LMS and you download them. But usually we have these kind of level markers which we introduce along the river, maybe along the banks or through the piers or other structures that are available. We read the values of depth from these gauges, and then we go back to our rating curve and calculate or measure the discharge. For example, these are few figures where certain gauges are being installed along the banks of the river. Then we have, if you do not have very defined banks, then you can have structures which are erected in the river stream and which contains the gauges, and we can read the values there. You can also see gauge installed here. These are again different kind of flow gauges. Groundwater gauging stations are also installed, but this is not the part of this lecture, so I'm not going into the detail of how to measure the groundwater depth. Okay. Annual hydrographs of different hydrological regimes. By just calculating, once you have all the discharge data and you plot the data as a time series for fairly long period of time, by observing the discharge time series you can say something about the catchment or about the area that it is draining. For example, if we look at this first time series, we have from January to December 1 year of data for a particular year. By the way, I have copied this figure from the Applied Hydrology book, which I have referenced in the initial slides. This is the scan from that book. Anyways, so this is all of these figures are showing the discharge data for one particular year, and you can see the differences there. Yeah, the first one, when we look at it, you see that you always have a certain discharge. The discharge on y-axis is in cubic feet per second, and you can see that if you can draw an average line, you would see that you have a particular value which is around, let's say, 50 cubic feet per second of water that is always flowing in this river, which means that it is a perennial river. There is always certain kind of flow here, and we have a defined wet season, and then there are also certain storm periods which are occurring in the particular months. So you can have an idea about the rainy season and the dry season, but anyways, it's a perennial river where there is always flow and which reacts to the different precipitation events at different times. Then we have ephemeral kind of rivers where you have discharge only in particular months of the year. Again, for the same year we have another river, and you see that January, February and March there is no flow whatsoever, and then the flow only starts showing up when there is a certain precipitation event, for example. Or maybe there is a dam somewhere and that dam has opened its spillways, and those spillways, the discharge that is going through those spillways have shown up here. But this is not a perennial river. There is no flow in certain part of the year, and then there is flow at other parts of the year or other times of the year. Then we have time series of discharge which shows something like this. For example, this is particularly a snow-fed area where there is a consistent flow of water that is being drained by the the amount of snow that is stored there in the catchment, and only in the summer months when the melting rate is high, we have a higher discharge that is being shown in, let's say, May, June and July months. So these are different kinds of annual hydrographs of different hydrological regimes, showing us different figures. We already went through the components of the hydrograph. We said we have a kind of decreasing, initially decreasing curve of water, base flow recession, then we have a rising limb, a falling limb, and then again reaching back to the base flow. We already discussed this part where we said that the precipitation that is falling on a certain surface would reach the discharge through different mechanisms, either through the surface, through the interflow, or the groundwater flow. So basically that is a figure which is referring to the initial picture that we showed in the initial graphs. There are different separation techniques for the base flow, separation of base flow from the direct flow or the surface runoff, because sometimes we have to find out that if there is a precipitation event, then that precipitation event would be contributing to a certain surface runoff, and what is that surface runoff? So we have to reduce, or we have to deduct the base flow out of it, so that we can know that that precipitation event alone has created that amount of surface runoff. This is not a topic at this level, separation of base flow components of a flood wave, but just to let you know that there are different methods available where we try to isolate the reaction of precipitation from the consistent behavior of a river. Also, as we looked at the earlier graph where the time series showed us what kind of catchment that is, in terms of whether it's a perennial river or a river which is just flowing for a few months and then it is dry. You can also have an idea of the size of a catchment by just looking at the hydrograph. For the smaller catchments, we usually have a very quick reaction time, so you would be having a very marked increase and then a decrease of the base flow. And then if you have a very large catchment, then you would be seeing something like this, a hydrograph which has different peaks. And it is for you to think about why do we have different peaks when we have, or let's say, why would a catchment show different peaks for a certain precipitation event. So that is for you to think about. In the next class, we will discuss again the other parts of this lecture. Till then, Allah Hafiz and best of luck.